Okay, can you hear me? Okay, can you hear me? Okay. So you want me to do question 19 and 22? Hold on. Oh, maybe I have it right here. No. My computer is not very good, so you're gonna have to just bear with some lag here. But once we get going, it should be fine. Let me know if I'm too loud, too quiet, or whatever. Oh, you can see my whole screen. Oh, geez. That's fun. I guess that's what I wanted. Mm-hmm. Okay, so question 19, the question that says 18 people are about to play a baseball game with 9 people being on each team. Is that the one you mean? Black Bear, whoever you are? Can you hear me still? Okay, all right, so we have 18 people and we're gonna make 2 different teams of 9. And then there's 2 people, A and B, who want to be on the same team. So because it's a probability question, the first thing we should do is count the sample space. So in general, what we're doing is we are taking 18 people and making one group of 9. And then the remaining 9 people make the other group of 9. So that math there will give us the sample space. I'm not updating this current screen. I don't know why you're still seeing that. Oh boy. Hang on a second. Okay. I'm sorry. Oh boy. Mm-hmm. Mm-hmm. Okay, we're back. I assume. Okay, I'm hoping this works. Okay, so back to question 19. So we have 18 people, and we need to make a group or a team of 9 people. And then there's 9 people left, and we need to make a group or a team of 9 people. So that math there will give you the sample space, because that's all possibilities without considering any special situation. So 18 choose 9 times 1. So there's 48,620 ways of just dividing the people into 2 groups. Then the event space, I need to consider the fact that there are 2 people, A and B, who want to be together. So I'm going to put them on the same thing. And I just noticed it's still not updating. Let's try that. Oh, finally. Yikes. Okay. So the sample space is 18 choose 9 times 9 choose 9, which is that 48,620 number. And then the event space. So in the event space, we have 2 people who want to be together. So 2 choose 2 is those 2 people who want to be together. And then that means there's 16 people left. I need 7 to complete the first group of 9. And that leaves 9 left to make the last team of 9. So this would be 2 choose 2 times 16 choose 7 times 9 choose 9. And that gives me 11440. So the probability is 11440 over 48,620, whatever that reduces to. Okay, so the next one I was asked to do was question 22. If you see my pen glitching, it's the memory on my computer being angry at me. So question 22. Okay, so 30% of students entering university will fail out in the first year. Boy, this is stuff you love to hear, isn't it? And 82%, okay, so just making sure I know all that. Okay, so in question 22, so in order for someone to get to graduate, there are 2 events that need to happen. Event 1 is they need to finish first year. And event 2 is then they need to graduate. So the probability that they finish first year, so we are told in the question that 30% fail out. So therefore, 70% will finish first year. Then if they finish first year, we're told that there's an 82% chance that they'll finish the whole thing. So 82%. So it's conditional. So I'm basically using the idea, the probability of A, oh, forget it. I'm just using fundamental counting principles, what I'm doing. So I do just 0.7 times 0.82, which is 0.574. All right, what's next? Should 34F be quantitative? Let me see, 34F. Preparation time? Yes, that is a quantity. Thank you. That is a quantity. Can you take up 17 and 22C? I just did 22. Didn't I? Yeah, I just did 22. Okay, and then 22C. 22 doesn't have any parts. Do you mean 21C? And by 17, do you mean the Venn diagram question? Because I've corrected the numbers, so I'm using a corrected numbers one. So try to give me the corrected numbers. So Hubert, by 17, do you mean the languages person? And then 22C, 22 doesn't have any parts to it, so I'm not sure what you mean. Oh, I hope you guys just didn't hear me drinking. Okay, 21. 2 dice are rolled. So 21C, 2 dice are rolled. So determine the probability that when 2 dice are rolled, the sum is 10, given that neither dice shows a 6. So think about, we know that when we roll 2 dice, there are 36 possible outcomes. So we could roll a 1, 2, 3, 4, 5, or 6. We could roll a 1, 2, 3, 4, 5, or 6. And so that means that a 1 and a 1 is a roll of 2. This is a roll of 3, and so on, right? You've seen this before. I believe this is given to you on the exam, and if it isn't, oh dear, that looks like Sanskrit or runes. If this isn't, you know, I forget if we put this on the first page or not. We meant to. So if it's not there, we'll just put it on the chalkboard. So that, you know, there's no point in wasting time you writing down numbers. I know that you know how to add, unless Michael's here, in which case, I don't know. Okay, so those are the 36 things that can happen when you roll 2 dice. Now, in this question, part C of it says the probability that the sum is a 10, given that there's no 6 on the dice. So if there's no 6 on the dice, I'm going to completely remove all of the possible outcomes that represent a 6 on the dice. And that leaves me with what's possible. And so there's 25 things possible. Of those 25 things, only one of them is a sum of 10. So 1 out of 25 is the conditional probability. How do you kick someone out of chat? Does anybody know? Ayano. Right. So what else am I taking up? Any other questions anybody wants me to take up? Can you do the languages? Yep. Sorry. The languages question. Okay, so we have 40 employees, 27 speak French, 11 speak Spanish, 7 speak Hindi. There are 5 Spanish speakers who also speak Hindi, and 6 Spanish teachers who also speak French. 3 of the French speak Hindi. 2 speak all 3 languages. Illustrate with a Venn diagram and determine how many people do not speak any. So a lot of numbers there, but obviously the most important thing on the first read through is that what we have is 3 different characteristics: French speaking, Spanish speaking, and Hindi. And then we need to make a Venn diagram. So let's start building up our Venn diagram. So boom, we'll call that the French circle. Boom, we'll call that the Spanish circle. And boom, that would be for the Hindi speakers. And then we put a box around it because we need to, there's only 40 people in this Venn diagram, not the entire universe. So the first thing we look for is a number we can write. And the only number we can write straight away is that there are 2 employees who speak all 3 languages. So 2 employees speak all 3. And then we basically work backwards. So 3 people are French and Hindi speakers. So I've already counted 2, so there's 1 more person. Then There are 6 Spanish teachers who also speak French. So these Spanish speakers speak French, but there's 4 more for a total of 6 Spanish-French. Then working backwards, 5 Spanish teachers who speak Hindi. So right now I have 2 of them, so I need 3 more. And then as I keep going backwards, so in total, there are 11, wait, where am I? 27 of the employees speak French, 11 speak Spanish, and 7 speak Hindi. Okay, so 7 of the employees speak Hindi. I've already counted 6, so there's 1 more. 11 speak Spanish, so I've already counted 9, so there's 2 more. 27 speak French, so I've got 7 represented, so there's 20 more. And then because there's supposed to be 40 employees in total, 24, 26, 30, there's 33 people in these Venn circles, so there must be 7 out here. And I believe the question said, how many employees do not speak any of those 3 languages? So the answer is 7. Number 20, with the probability of A and probability of B, independent events, mutually exclusive events, and so on. Okay, so part A says find the probability of A and B if A and B are independent events. So what makes this, one of the more complex parts of combinatorics is that we use this symbolism and the idea of intersection, whether it's the intersection of 2 characteristics in a single event or the intersection of 2 events. In part A, we are specifically told that A and B are independent events. So A and B are 2 different events, and we want them to both occur. So that means we want this to occur, it has a 14% chance, and this to occur, it has a 27% chance. So if I need them both to occur, then I need first this event to happen, and then this event to happen. So it's basically a fundamental counting principle idea, and is very similar to the question I took up earlier about the probability of graduating university. So because they're 2 different events, and they're independent, meaning that there's no, the 0.27 for B is true no matter what happens with A. Then part B of the question, we're now talking about mutually exclusive events. And so we want the probability of A union B. So the issue here is that the definition of mutually exclusive is that they cannot possibly both happen. So instead of in part A, where we used event 1 and then event 2, we can't multiply these numbers together here because they're mutually exclusive, meaning it is literally impossible for them to happen at the same time, which means the only way for them to both happen is if A happens or B happens. So I need either this to happen or this to happen. So again, that's really the key difference between, like, when am I multiplying, when am I adding? I'm adding because I want this one or this one. Whereas here I want this one and then this one. So because they're mutually exclusive, I'm going to add them together. So that's 0.41. And then in part C, we want the probability of A union B not, and we're told that the probability of A intersection B is 0.1. So in order to find the probability of A union B not, I'm going to start by finding the probability of A union B. So this is what we have a formula for A union B. It says add them together, like I did in part B, add them together, except for in this question, when I added them together, they were mutually exclusive, so I didn't have to worry about any overlap. I didn't have to subtract. But now in part C, there is an overlap. There is an intersection. So I have to subtract the 0.1 because it got added together in both locations. So now I'm going to do 0.14 plus 0.27 minus 0.1, which is 0.31. But that's the probability of A union B. And again, that's one of the formulas, by the way, on your formula, the formula part. And then therefore the probability of A union B not is 1 minus that, which is 0.69 or 69%. Verify if 37 has the correct answers. Oh, bro, yeah, 37 is blessed. Actually, I'm not sure. I'll just go through them really quickly. In part 1, so we're identifying sampling methods, right? So when I look at this, the list of numbers in part A, I notice that I have A, 9 and 24, B, 9 and 24, C, 9 and 24, D, 9 and 24, E, 9 and 24. That's not going to happen with any sort of like completely random thing. There's some structure here. I have the exact same amount from every group, A, B, C, D, E, and then I've also taken the exact same person. And the only way for that to happen is through systematic random sampling. B, so if we look at B, I've got 1 from A, I've got 3 from B, 2 from C, and 4 from D. So like, it's clearly like, there's no evenness here, that there's no pattern here. There's no balance here. There's nothing here that indicates that there was any structure done to the data. So this is just simple random sample. In C, you'll notice they're all from B. There's only 2 ways to get all from B. There's only 2 ways to see a single group represented like this, either cluster, where you have to take all of them, or multi-stage. Now, clearly I did not take every kid from class B, which means that must be multi-stage. And then D, so I've got 2 from A, 2 from B, 2 from C, 2 from D, 2 from E, but they're not in the same step count arrangement that A is. So I took 2 from here, 2 from here, 2 from here, 2 from here, and so on. That would be stratified because I'm taking a proportionate amount from each class. Okay. Can you do 10A? Let's see what's going on here. A family of 7 made up of 2 parents and 5 children. The parents must sit on the ends. So we've got 7 people. And they're just going to sit in a row, which is normally 7 factorial. But in this case, 2 of the 7 must sit on the ends. So I must have one of the parents here, so that's 2 choices, and the other parent here, that's 1 choice. And in between them are going to be 5 people, 5 kids, so that's 5 factorial. So 2 times 5 factorial times 1, which is, I think, 240. 17. I just did 17. 31B. Determine so we have these computer chips that are failing. Chip A has a 10% failure rate and chip B has a 7% failure rate. Determine the probability that at least one fails. So at least one fails. So I could either have this, so we have 2 chips, A and B. So if I want at least one to fail, I need this one to fail and this one to work, or this one to work and this one to fail, or both of them to fail. So all of those cases represent at least one failing. So it's not too onerous to go through that. So the first one has a, let me just check the numbers here. The first one has a 10% failure rate and a 7%. So if the first one fails, that happens 10% of the time. The second one fails 7%, so it works 93%. So that's the first one. 0.1 times 0.93. So 0.093. Again, the glitchy plan is because of my old computer. This situation where I want the first one to work, there's a 90, come on, 90, now it's not working. 90% chance of the first one working and a 7% chance of the second one failing. So 0.9 times 0.07 is 0.063. And then if both of them fail, that's 0.1 times 0.07, which is 0.007. Add them all together, and you get the answer. But there's another way to do the question. So the opposite way of doing the question is the opposite of at least one is that none of them fail. And for none of them to fail, I would need the first one to work, which is 90%, and the second one to work, which is 93%, and then subtract that from 100%. That gives you the same answer. Can you do 28? '28 is one of the videos I already have up. So you can just watch the video on that, Eileen. The committee of 6 students. I made some quick YouTube videos. All right, Sam, please take up 3 and 7. Oh, I'll be right back. Talk amongst yourselves. My cake is done, and I gotta go get it out of the oven. 1 second. 1 second. Okay, cake is rescued from the oven. I'm back. What was I doing? Oh, I was looking up 3 and 7. 3. Here we go. Where's my stylus? Uh-oh. 1 second, equipment failure. No, okay, we're good. Okay, so we have 4 songs and 2 piano collections. So we have 6 things. So, always take a step back from a question that you're not sure what to do with and just, what is this? Well, this is a 6 things that need to be arranged in order question, which is fundamental counting principle, which can lead itself into factorial permutation, whatever. But fundamentally, I have 4 songs. and I have 2 piano things. Now these are different songs and different piano things. So it's not like rearranging the letters in the word career. They are different songs, but you know, so if I just said how many ways can I arrange it, I would just say 6 factorial, but there's restrictions. For example, we have to have a song here and we have to have a song here. So that means I'm gonna pick those things first. There are 4 songs that I could pick to go there, and there are 3 songs that I could pick to go there. So far I've got 12 choices to make, 4 times 3. Then what I know is that the piano pieces, these 2 piano pieces, cannot be side by side. Now there's only 4 places to worry about. So this is actually, you know, one of the times we can actually just think about the whole picture. The piano can go here and here, or piano can go here or here. And the only other thing is the piano can go here or here. There's only actually 3 configurations as to where the piano pieces can go, because there's only 4 slots anyway. So I'm gonna say, for example, do all my math as if I was putting piano, song, piano, song. So I'm gonna do my math here, and then I can just multiply by 3 because there's only 3 different ways that those other piano things could have been. So if I put a piano here, I've got 2 piano pieces and 1 more piano piece for this position. Now, after placing the 4 songs here, 3 songs here, I've got 2 songs here and 1 song here. So if I have exactly song, piano, song, song, that is 4 times 2 times 2 times 1 times 1 times 3, which is 4 times 2. 16 times 3 is 48. How come all my pens didn't work? So if we just look at this one, 4 times 2 times 2 times 1 times 1 times 3, right? 16 times 3, 48. And then you say, okay, well, that's in the PSPS configuration. It could have also been this one or this one. So then I'm going to multiply by 3, and then that would be the answer. Wow, I'm not very happy that you would log on with that username, somebody. Sam, you also asked for question 7. How many 4-digit numbers less than 8,000 contain at least 1 9 if repetition is allowed? Okay, so again, we'll start with the thinking about the question in its most basic setting. So we want a 4-digit number. So that means I have 4 decisions to make about the numbers. Now it has to be less than 8,000. So less than 8,000, like the highest it can possibly be is 79999. So this number here that it starts with can be a 1, 2, 3, a 4, 5, 6, or 7. It can't be a 0 because if it starts with a 0, it's not a 4-digit number. It could be a 4-digit passcode or a 4-digit license plate or whatever, but it can't be a 4-digit number. So I have 1, 2, 3, 4, 5, 6, 7 choices as to what the number starts with. Now, the question says that we need the number to contain at least 1 9. So this is definitely one where you want to do the opposite. We're going to count all possible numbers and subtract the ones that have 0 9s. So all possible numbers that are the 4 digits long, less than 8,000, would be 7 times 10 times 10 times 10, because repetition is allowed, and you can use anything 0, 1, 2, 3, all the way up to 9. So there's 7,000 numbers that are less than 8,000 and 4 digits long, which should make sense anyway. And then if I want no 9s at all, so I'm going to ban 9s from my number, there's still 7 choices for the beginning because 9 was never allowed. And then instead of 10 choices, I only have 9 choices because I can take a 0, 1, 2, 3, 4, 5, 6, 7, 8, or that's it. And then times 9 times 9. So again, I've banned, the number 9 is not a choice, which means I have 9 choices. So 7 times 9 times 9 times 9, whatever that is 5103. Oops. So of the 7,000 numbers, 5,103 of them have no 9s whatsoever, which means the remainder of them, by subtraction, will have at least 1 9, 1897. Okay, what's next? Where am I scrolling? I don't even see. Okay, So I see 52 next. Please take up question 52. There's 20 people interested in representing a school at the bike event. 6 are teachers, 4 are students. We want to create a probability distribution for Y, the number of teachers, and calculate expected value. Okay. So we have 20 people, and that's made up of 6 teachers and 14 students. And what are we doing? So Y is the number we're going to randomly select and to make a group of 3. And then we want to look at the probability distribution. So Y, again, the number of teachers. If it's a group of 3, you might have no teachers. You might have 1 teacher, 2 teacher, or 3 teachers. So now I'm going to calculate all those probabilities. So our sample space is that fundamentally what I'm doing is I'm choosing out of 20 a group of 3. So that's my sample space. 20 choose 3, which is 1140. And then, for example, in the first one, my event is no teachers. So out of the teachers, there's 6 teachers and I don't want any, which means out of the 14 students, I need 3. So 14 choose 3 is 364. So the probability of 0 teachers is 364 over 1140, and you would just do the rest of the question similarly. And then expected value, you would just be taking this times this, and then adding all those things together. Oh, sorry, I didn't want to take up 52 because I'm really displeased that you would log on to a Scholastic thing with that username. You need a professional username when you're dealing with professional things. You should know that. You're getting into grade 12. Alistair, can you take up 25? 4 heads are rolled. What is the probability that at least 2 of them roll the same number? So I did a video on this one, right? Did I do a video on this one? I'll just go through it really, really quickly. Basically, you have to do this one the opposite way. There's no way. I mean, there is always a way, but you're not going to do it by saying, well, 2 could be the same, or 3 could be the same, or 4 could be the same. Like this one's pretty easy, but 2 could be the same, you know, first and second, first and third, first and fourth, second and third, second and fourth. Like it's just way too much. The way to calculate this one is to do the opposite. So the opposite of at least 2 are the same is none are the same. So we're going to calculate the probability that we're going to roll that dice 4 times and none of them are the same. So first the sample space. So if you roll the dice, there's 6 things. So each person can see whatever outcome they want because that's just the sample space. So there's 1,296 possible outcomes. So now I'm going to count the opposite of the question, which is everyone has to get a different number. So the first person, well, they can roll whatever the heck they want, 6 choices. The next person cannot match that number, so they only have 5 choices. The next person cannot match either of them, so they have 4 choices, and then 3 choices because they can't match. So if I'm not allowing anyone to roll the same number, there's 360 outcomes, which means the probability of my event where I do let people get the same number is 1 minus this probability. For question 10A, the answer is 120, but you got 240. The answer back correct. Go with 240, I guess. You could use a tree diagram in a lot of questions. Basically, anytime I'm multiplying numbers together, I'm choosing to not draw a tree diagram instead, but certainly whenever there's just a small number of events, like 2 events, you'd use a tree diagram if you want. Yeah, Sam, if there were more slots, like let's say that I had 52 songs and 2 pianos or whatever, what you would do is you would count the opposite. So you would put the piano pieces together, like glue them together and treat them as one unit, kind of like we do when we make 2 people stand together side by side in a lineup, and then mix them around as if they're the same person or the same piano piece or whatever. And then that's the opposite of what you want. So it's just like 2 people having to, I don't want 2 people to stand together in a line. So I count all the ways where they must sign it. Actually, I'm confusing myself. I'll just show you what it would look like. Clear board. So going back to that piano thing. So let's look at the middle section where we had 2 songs. So song 1, song 2, piano 1 and piano 2. So the other way we could have done it is we could have, well, we don't want these piano things to be together, but I'm going to make them be together. So I'm going to make them be together and treat that as one thing. So I have 1, 2, 3 things, which is 3 factorial. These could have been organized in 2 different ways. And that's the opposite of what I want. So in total, there were 4 things. So you can always do it by subtraction. Why don't you ask that other math teacher, Michael? The one you said was the best? Help with 53. Uh, 53. Every time a sunflower seed is planted, there's a 22% chance that it will fail to grow into a sunflower. And we've just planted 85 seeds. What is the probability that exactly 20 will fail to produce? So this feels like a binomial question. Ooh, so let's see. We are planting 25 seeds. So every time we plant a seed, that's a trial, and we're doing 85 trials. Okay. There's a 22% probability of success. I'm going to define success to be, weirdly enough, failing to grow. Because again, success doesn't mean a good thing. It just means the thing I'm looking for. And that 22% apparently is the same every time. So this is a binomial experiment. So we want the probability that exactly 20 out of 85 have this success. So the probability of exactly 20 successes is, out of 85 attempts, we want 20 successes. The probability of success is 0.22. We need 20. The probability of failure is 0.78. We need 65. And again, make sure you are calculating that all directly into your calculator. Michael, I'm allowed to diss you. I'm your teacher. Like I'm totally giving up my free time to help you with an exam. So yeah, you're going to get dissed. That's how it is, man. So when I type that all in, and again, try to type it all in at once, I get 0.09593, whatever. That's part A. It was exactly 20. Now, part B says, what is the probability that more than 20 will fail? So more than 20, ooh. So more than 20 means 21 or 22 or 23 or 24, all the way up to 85. So I really hope we'll be able to use the normal approximation method, or we're going to be here for a long time. So let's make sure that n times p is greater than 5, and let's make sure that n times 1 minus p is greater than 5 so that we can use this method. So n times p is 20 times 0.22, which is, wow, you'd think I would know something like that. 4.4, oh no, what? 4.4, is it really? Sorry. 85 is n. N is 85. We're planting 85 seeds. So 85 times 0.22 is 18.7. That is greater than 5. And then 85 times 0.78, probability of failure, is 85 times 0.78, 66.3. That is also bigger than 5. So we are allowed to use the normal approximation method. Just a reminder that you have to show those tests to get full marks. So now that we know that we're allowed, let's do the calculations. We need to calculate x bar. X bar is n times p. We just calculated that and I erased it. So yay. It is 18.7. And then the standard deviation is the square root of n times p times 1 minus p. So it is the square root of 85 times 0.22 times 0.78. So 85 times 0.22 times 0.78 equals square root that, 3.82. And then the last thing we need to do is, because the question said, let me just double check here, more than 20. So I want 21 and upwards. So do I want, so more than 20, I don't want to include 20, but I do want 21.21. So obviously I'm going to take 20.5 because I do not want 20, but I do want 21 because I'm going more than that. Okay, so that means I can now calculate the Z score. So 20.5. Oh, sorry, glitch. 20.5 minus 18.7 divided by 3.82. That will give me my Z score. I should start like a Patreon to like buy me a computer with more RAM so it can handle streaming while I do this stuff. Anyway, I get 0.47. So on the Z score table, I need to look up 0.47. 0.47 on my Z score table, which I should have had in front of me. So when I look up 0.47, I get 0.6808. But that is just straight looking at the Z score table. So that is less than 20.5. So I need to do 1 minus that to answer the question. So I'm getting 0.31992. Where was I? Okay, so that was 53. That was Black Bear. Oh, but you meant 51. But I did 53. All right, 51. A game is played in which a 6-sided dice is rolled and a single coin is tossed. Players win the amount of money displayed by the dice roll. But when double that amount, if the coin shows heads, let X discrete random variable and then fair game. Okay, so 6-sided dice. If you get heads, you get double. Okay, boom. So for sure, and any of these questions where you're doing like a couple different things and you're winning money, plan ahead before you actually start creating your probability distribution. So for example, I know that if I roll a dice, there's 6 outcomes, and then tossing a coin, there's 2. So there's a total of 12 things that can happen. And so that's the sort of thing that we're going to give you on the exam in a question like this, because we want to make sure that if in doubt, you could simply just write out all possible outcomes and plan ahead. So if I roll a 1 and a tail, I could roll a 2 and a tail, a 3 and a tail, a 4 and a tail, a 5 and a tail, a 6 and a tail, or a 1 and a heads, a 2 and a head, a 3 and a head, 4 head, 5 head, 6 head. So there's only 12 things that can happen. So if I roll this, I get $1. If I roll this, $2, $3, $4, $5, $6. Here, if I roll the heads, I would double it. So I get $2, $4, $4, $6, $8, $10, $12. So those are all possible values of X. Oops, I wrote 10. So we can start to make the probability distribution because all my outcomes are in front of me. So the smallest possible value I could win is 1, and 1 out of 12 of my events shows that. I could win $2, and there's 2 different ways of getting $2. So that's 2 out of 12. I could win $3. There's only one way, 3 out of 12. I could win $4, and there's 2 different ways. So that's 2 out of 12, and so on. And then to do the answer, the second part about the fair game, because it's a probability distribution, you would do 1 times 1/12 plus 2 times 2/12, plus you would add them all together, and that's your expected value, also your fair game amount. Will you ever be forced to use a tree diagram? You could be. Like, there should be some questions where there's simply no other way. Can you do question 31? Let's see. Wait, I just did that one. The chips, I just did that one. 29. Oh, the boxes. Okay. 5 red, 4 yellow, 8 and 3. Okay. So in the first box, we have 5 red and 4 yellow. In this box, we have 8 green and 3 red, 8 green and 3 red. And we're just going to randomly choose a marble out of each one. So A says find the probability you do not select a red marble. So if I don't select a red marble, then that means here I need a yellow marble, which is 4 out of 9 likelihood probability. And then, so 2 different events, they both need to happen, multiply. And then to not get a red, I need 8, because I need a green, 8 out of 11. So that would give me 32 out of 99. And then the second part, it says you get a yellow from the first or a green from the second. So here are all the scenarios that satisfy part B. Oh, we're glitching pretty bad here. Sorry, glitch. Okay, so if I want a yellow from the first and a green from the second, I'd be happy with yellow and then not green. I'd also be happy with not yellow and green. And of course, I'd be happy with yellow and green. So one way to do it is to calculate all of those and add them together. But of course, the only thing I haven't written down here, the only thing that I'm not happy with is not yellow and then not green. So in other words, the only thing I don't want is red ball, red ball. So I'm just going to calculate that probability and subtract it. So 5 out of 9 likelihood of getting red, 3 out of 11 likelihood of getting that. And so if I calculate that, I've got the probability of yellow on the first or green on the second. 3129. I'll do my best to post this. You know, my computer seems to be momentarily, moment by moment, trying to crash on me, but I will certainly do my best. The practice runs I did, I think, posted automatically, which is pretty scary. I had to figure out how to delete them, but I think it will post automatically. I'll certainly, again, do my best. So I already did 22, so I don't want to spend a lot of time going over things, but so to graduate from university, you need to first get past the first year. Event 1 is finish the first year. Event 2 is graduate. So if 30% fail the first year, then 70% make it. And then right? That's a multiply statement. And then I need to then go all the way, which is 82%. So just multiply them together. 52. Okay, so, oh, I just did that one as well. Did you just show up? Because I did that one. So just really quickly, the sample space is that there's 20 people. We're making a group of 3. And then the probability distribution, the number of teachers could be 0, 1, 2, or 3, because I'm making a group of 3. So you might get no teachers, 1 teacher, 2 teachers, 3 teachers. So for example, the probability that I get 0 teachers would be, well, first from the 6 teachers, I need to choose nobody, which means from the 14 students, I need to take 3. That's my event space. And I would divide by my sample space. And then you would just go from there. So 1 teacher would be 6 choose 1, and 14 choose 2, and so on. And then 55. There is no 55. 54. Board game. 2 dice are used to move players around a map. If they roll doubles, they receive bonuses. In a particular game, they will have to roll 24 times. How many doubles can they expect to roll in 24 attempts? So this is a binomial experiment. So we're going to do a trial 24 times, and 1 trial is rolling 2 dice. Every time I roll the dice, I know I can calculate the probability of rolling double is 1 in 6, or 6 in 36 if you prefer, but it's 1 in 6. And that doesn't change no matter what happens. So this is a perfect probability distribution, or binomial probability distribution. So let's look at how many can you expect to roll. So because it's a binomial experiment, the expected value can be calculated quickly using n times p, which is 24 times 1/6. Probability of rolling doubles. So you expect, oh, nope, I can't do math. You would expect 4 doubles in that game. Question B says, what is the probability they roll exactly 5 doubles? So exactly 5 doubles. So exactly 5, we're going to consider doubles to be success. So out of 24 attempts, we want 5 to be successfully doubles. So 1/6, that's the probability of success, and I need 5 of them. The probability of failure is 5/6, and I need 19. So again, be careful here. Do not attempt to use 1/6 as a decimal. Make sure you're typing it in as a fraction. So 24 choose 5 times 1/6 exponent 5 times 5/6 exponent 19. Oh, I just cleared the whole screen for no reason. 1/6 exponent 5 times 5/6 exponent 19. So that doesn't make any sense. Sorry. You don't even know what I typed in or what I saw, but I promise you it was not correct. Because we know a probability has to be between 0 and 1, and that answer was not. There, that's a better answer. So it's about 17%, 0.711. And then part C says, what is the probability that they roll 2 or fewer doubles? So don't be tempted here to use the binomial approximation because it says 2 or fewer. If you attempted to, refer you back here. N times P is 4. You cannot approximate. So you have to do, for 2 or fewer, you have to do none of them. Add to that 1. And add to that 2. There's no way other than just straight up do all 3 of these. So you would do it kind of like the one we just did. Probability of 0 is 24 choose 0 and then 1 over 6 to the 0, and 5 over 6 to the 24, plus 24 choose 1, 1 over 6 to the 1, and 5 over 6 to the 23, plus 24 choose 2, 1 over 6 to the 2, 5 over 6 to the 22. Question 19 and 20. Oh, I did both 19 and 20 already. The baseball one and the independent events, mutually exclusive events. 54 and 51. What's 54? Oh, the one I already did, right? Yeah, I did those. Yeah, man. See ya tomorrow, Michael. Come early for that calculator, yo. $41. You want me to do a statistics question? Do you mean 42? Like, I'm not just gonna, because I mean, I can't really show you typing into my calculator. Do you mean the one that's grouped? Like, or just straight up a stats question? I guess, you know, let's do the stats one because, you know, it's good to review like the outlier stuff and all that. So question 41 gives us a bunch of numbers. In fact, it gives us 15 numbers. So I'm not going to go through mean and IQR because, sorry, I'm not going to go through mean and standard deviation because that's just done in your calculator. And everyone has different calculators. But let's look at median and standard median and IQR. And outliers and stuff. So if we have 15 numbers, let's think about where we would find all of our interesting pieces of data. So I'm just going to put 15 marks on the board to represent 15 pieces of data. 1, 2, 3, 4, 5, 6. So there's 15 pieces of data. So the middle piece of data, because it's an odd number, we can find it exactly. So the middle piece of data is going to be the 8th piece of data. And so you can count 7 from the front, 7 from the back, and you would get here. So if we look at the data, if I count 7 from the front, this 360 number, and if I count 7 from the back, 1, 2, 3, 4, 5, 6, 7, then the next number is 360. So the median is 360. And so once you have the median, to find interquartile range, so here is the first half of the data, and here's the second half. So because this piece of data here, the median, it's not between two numbers, it is a number. So it's not in the first half or in the second half, it's right in the middle. So it doesn't count as first half or second half. So in the first half, I have 7 numbers. So again, pretty easy to find the median of 7 numbers. So if you count in, if you count in 1, 2, 3, the fourth, and count backwards 1, 2, 3, the fourth. So that's Q1. And the same thing here, count in 1, 2, 3, it's the fourth. Count backwards 1, 2, 3, it's the fourth. There's lots of different ways of doing it. So if I could look at my actual data, if I count 1, 2, 3, then 199 is that fourth number, which is Q1. So 199. And then if I also from the back end go 1, 2, 3, the fourth number from the other end is 614. So there's Q1 and Q3. So if I subtract them, I will get the interquartile range, which is 415. So I need this and both of these numbers to do the outlier boundary stuff. So what I need to do is I need to do 199 minus 1.5 times 415 to see where my lower boundary is. So 199 minus 1.5 times 415. So any number smaller than negative 423.5 is so small. Basically, it's saying it's so far away from the median and from the middle of the data that it's too small. It's an outlier. There's obviously no outliers on that side. To calculate the upper outlier, so 614 plus 1.5 times 415 would tell me if there's an upper outlier. So any number greater than 1236.5, and of course there is no data bigger than that, so there's no outliers. And so that means that the smallest piece of data and the biggest piece of data, neither of them are outliers. So when I go to draw a box and whisker, I don't have to worry about putting stars anywhere. If the number of pieces of data was even, so like let's say instead of 15 pieces of data, let's say I had 14. So first I need to find the median. So 14 evenly divides by 2. So I'm going to draw a line to divide first half, second half. To find the median, I take the midpoint of these two pieces of data. So the midpoint of the 2 in the middle, that would be the median. And then you can clearly see that that line has also divided my data into first half and second half. So Q1 is right here because I got 3 and 3. So like visually speaking, as a very visual learner, being able to actually see the symmetry that happens when you do this properly. So here's Q1 and here's Q3. Now, what if I had 16 pieces of data? It's not exactly the same. So if I had 16 pieces of data, 7, 8, 9, 10, 11, 12, 13, 14. So again, the median, 16 divided by 2 is exactly 8. So 1, 2, 3, 4, 5, 6, 7, 8. And then 1, 2, 3, 4, 5, 6, 7, 8. So it's perfectly split in 2, which means I need to take these two pieces of data, add them together, divide by 2 to find my actual median. And now the first half of the data, there's 8 pieces of data, 1, 2, 3, 4, 5, 6, 7, 8. And again, if I divide that in 2, I get exactly 4 pieces here and 4 pieces here. So Q1 is actually halfway between whatever these two numbers are. Same thing over here, 1, 2, 3, 4 split, 1, 2, 3, 4. So Q3 is exactly halfway between these. And so again, visually speaking, you can see I've got 4, 4, 4, 4. I've perfectly quartered my data. So in question 42, because the data is already grouped, excuse me, you use the midpoint of each group. So the information given, it says that between 10 and 15 minutes, there are 2 pieces of data. So in fact, what you use is you pretend as if it said 12.5, 2 pieces of data. So you just have to treat every one of these pieces of data as if they're halfway between 10 and 15, which is 12.5. And in the next category, 15 to 20, halfway between, would be 17.5. So you treat all 20 pieces of data as if they were 17.5. Excuse me, and so on. One C and one F. So in the word Kaladin, oh, here, let me try that again. Kaladin. So I want to rearrange all 7 of these letters, but, and none of them repeat, so that's kind of nice, except for in this particular one in 1C, I want the A, the E, and the O to be grouped together. What's this? I don't know. What's this? Uh-oh. What's happening? Why did this happen? What is happening? Sorry. I lost my whiteboard. It's okay. You're just watching me lose it and bring it back, I guess. Okay. Okay. Okay, so again, the word Kaladin, I think it crashed because I had actually written something legible and my computer didn't know what to do. Message retracted. Red, what did you say? I hope it was not rude. There's enough rudeness on the internet. Okay, so we want to rearrange those 7 letters, but we want the A, the E, and the O to be grouped together. So I'm going to take the A, the E, and the O, and I'm going to glue them together, and I'm going to treat them as a single item. So now what I'm rearranging is this thing, the C, the L, the D, and the N. So I'm considering myself to have 5 different items, and I want to rearrange 5 items. This is a super big item, and it's got problems. We'll deal with it later. But right now, I'm just going to say I have 5 items, and I want to rearrange them. That's 5 factorial. Now, every single time I rearranged this whole massive box AEO, I could have paused my 5 factorial and said, well, AEO didn't have to be in that order. It could have been in any order within those 3 items, which means that there is 3 factorial more rearrangements I could have done, because every one of these 5 factorials could have then had 3 factorial more on top of it. So that's 120 times 6, whatever that is. 1F. There are 4 letters in length and contain at least 1 vowel. So again, if I'm rearranging the letters in the word Kaladin, they're all different. And so I want to create only a 4-letter word out of them. And I must have at least 1 vowel. So, you know, again, we've done so many questions. I hope it's pretty obvious that the opposite of at least 1 is no vowels, and it's going to be way easier to calculate that. So I'm going to calculate the total number of 4-letter words, which is 7P4, because there are 7 unique items and 4 positions. And from that, I'm going to subtract all the words made up only of the non-vowels. So C, L, D, and N. So there's only 4 of them and only 4 positions. So if I do P7-4 minus P4-4, again, this is no vowels. What I'm left with must have vowels. 3. I'm starting to repeat questions, so well, let's see. Okay, so just really quickly, the piano song again, the piano and song question again. So you have to have a song here and here. So there's 4 choices, and then there's 3 choices. In here, I need to have 2 pianos, but they can't be side by side. So for example, I could have piano here, and song here, and song here. And if I did that, I would have 2 choices, and then 1 choice for those piano, 2 choices, and then 1 choice for the song. So right now, if I do that, it's 4 times 2 times 2 times 1 times 1 times 3. But I didn't have to have piano, song, piano, song. I could have had piano, song, song, piano. Or I could have had song, piano, song, piano. So in fact, there are 3 different ways I could have had this initial grouping. So take that and multiply by 3. 6C. Oh, so 6C, there's a video up on my YouTube page. So you just check that one out. Because it's an annoying question and I don't want to do it again, but there's a video that is much easier to read than what's happening with my computer right now. So go check that out. So just really quickly again, all possible numbers less than 8,000 that are 4 digits long. You have 7 choices here because you can't start with a 0, 8, or 9. Then all possible numbers, so ignoring any restrictions, letting any number happen, there's 7,000. And if I want to have at least one 9, the opposite is no 9. So if I'm not allowed a 9, then there's 9 choices, 9 choices, 9 choices. That would give me the opposite, and then I would just subtract. 18B. 4 cards are dealt from a standard deck of 52. Determine the probability that all 4 are red if cards are not replaced after being drawn. So we are drawing 4 cards from a standard deck of 52, and we're not replacing. So let's do sample space. So 52 cards, and then 51 cards, and then 50 cards, and then 49 cards. You can also calculate that a little quicker by doing 52P4. That's the sample space of the question. Now, the event space, I'm interested in is that, what is it? All 4 cards are red. So initially, half the deck is red, which is 26 cards. And then I'm only allowed to take from the red, so 25, 24, 23. So you can also quickly calculate 26P4, and then this divided by that. 18B. Oh, I just did 18B. Coolio. All right. So 44 is a weighted mean question. So the first thing you have to do is calculate the percentage. So like for Emilio, in originality, he scored a 90%. In presentation, he also scored a 90%. In methodology, he scored an 85%. And in community impact, he scored a 95%. And then the weighting of each one is not the same. So this is a weighted average. So 20, 30, 35, 15. So this one's worth 20%. So I'm going to multiply by 20. This one's worth 30%. This one's worth 15. And this one's worth, no, sorry, this one's worth 35, and this one's worth 15. So I multiply them using the formula for weighted mean. 0.9 times 20 plus 0.9 times 30 plus 0.85 times 35 plus 0.95 times 15. So he actually scores an 89, and then you would just do the same thing with the other person and compare them. 47. So 47 is a probability distribution, and you could use a Z-score table for it, but clearly the numbers 68, 95, 99.7 are given for a reason. 45 and 8, 45 and 8, 45 and 8. So, you know, because I'm clearly trying to get you to think about the Z-score, the normal distribution. So the median is at 45. If I go up 1 standard deviation, that's 8 units higher, according to the question. So that's 53. Go up 8 units higher, and that is 61. Go up 8 units higher, and I am now at 69. Is that right? And then I'm going to subtract 8. So 54 minus 8 is 37. And then subtract 8, and I'm at 29. And then subtract 8, and I'm at 21. That doesn't feel right, but whatever. And then, so we know that 68% of the data is here, so that's 34%. And that's 34%. And then 95% of the data is here, so that's 13.5, 13.5. And then 99.7, that gives us 2.35, 2.35. And then that's 0.15, 0.15. So now I can answer any question. For example, between which two numbers will 68% lie? 68% will lie between 37 and 53. Between which two numbers will 95% lie? Between 29 and 61. Between which two numbers will 99.7% lie? 21 and 69. What percent will fall below 61? So below 61 is all the data below here. So I just add up all of these numbers, and that adds to 87.5. And then what percent of the data lies above 37? So here's 37, so above 37. So I want to just add all these numbers here. So again, if you could totally also do that question entirely with Z-scores. It would take longer, and you wouldn't get exactly the same numbers, but I would mark it right. But you really, that's a big time waster. You know, if I set up a 6895 question and you spend all the time doing Z-scores on it, but, you know, I mean, if you haven't properly memorized the 6895 stuff, I guess you're doing it that way, and hopefully you can still finish the exam. So for Miss Kwan, she has a mean of 32 and standard deviation of 4.5. So approximately normal. With a mean of 32 and a standard deviation of 4.5. And it says, what is the probability that on a particular day it takes her less than 25 or more than 40 minutes? So less than 25, so I want this data, or more than 40, so I want this data. So I have to do two separate things and add them together. So less than 25, Z-score 25 minus 32 over 4.5. Look up that Z-score. Oh, do I have a Z-score table? I'm not telling you how many pages the exam is because it's completely irrelevant. It's nothing that's going to be gained from knowing how long an exam, how many pages it is. It's 2 hours in length. That's what's important. So that's a Z-score of negative 1.56, which corresponds to 4.85%. So 4.85% of the time, which is right here, it takes less than 25 minutes. So now how much of the time does it take more than 40 minutes? So we'll use 40. Calculate my Z-score. And I get a Z-score of 0.44. Looking that up. 0.6700. But that 67% is below, so I need to turn that around. So that would be 1 minus that, which would be 33% above. All right? Yeah. Said score 0.44. Yeah, that makes sense. Yeah, so you would add these two numbers together to get below 4.85 or above 40. Okay, it's 8:30. There's not a lot of questions coming at me, and I think what's happening more often is people are looking for answers that I've already done, which means I should be posting this video so people can start to go through it if they really want it. Plus, you can tell by my voice, I'm just tired of talking, man. Tired of talking. Tired of it. Is that okay? I don't see anybody. Oh, right, there's a delay. Oh, no one's complaining, so bye. Click. See ya. Seriously, though, I can't even see how many people are in the chat. I mean, it looks like 3 people are in the chat, and I'm one of them because my other ID is in there. Can you go over question 5 quickly? A coin is tossed until a head appears or 4 total tosses have occurred. So, so this is one where you want the tree diagram for sure. It says it. So basically, because the problem is like, you know, how many tasks do I have? Well, it depends. So obviously I start by tossing a coin and either I get heads or I get tails. If I get heads, I stop and I'm done. If I get tails though, I got to keep going and toss it again. And I could now get heads or tails. If I get heads, I stop. But if I get tails, I keep going. Heads or tails. So if I get heads, I stop. If I get tails, I keep going. And this is now my 4th coin toss. So I stop no matter what. So this is one where you would need a Venn diagram, or sorry, a tree diagram, because the outcomes are very strange and difficult to count without this, because these are all possible outcomes. There are 1, 2, 3, 4, 5, 6 possible outcomes. Why did I? Heads, tails, heads, tails, tails, heads, tails. No, that's right, 5. Anyway, that's that question. Okay, good night to Blue Bob and Red and Hubert and Aaron and Sandy and Black Bear. Black Bear, man, you've been here for a long time. Anyway, I hope that was helpful. Please get a good night's sleep. And go Raptors. All right. Bye. Have a good night. Now I say that, and then I realize I have no idea how to stop this live stream. What if it just happens forever? Wait, does this work?